Okay, so today we're looking at a paper called End-to-End Test Time Training for Long Context. This one comes from a pretty heavy-hitting group of researchers. We're talking Asteria Institute, NVIDIA, Stanford, UC Berkeley, UC San Diego.
Yeah, and they're tackling the long context problem from a completely different angle than what we've been seeing with all the new architectural innovations.
It really feels like a paradigm shift. They're basically saying the answer isn't a new architecture, it's about reframing the whole problem.
Exactly. They see it as a continual learning challenge. So they take a standard transformer, nothing fancy, one with sliding window attention, and they just let it keep learning during inference.
So it's compressing the context directly into its own weights as it goes.
And that's the core method, TTTE2E, or end-to-end test time training. It's end-to-end in two ways. At test time, it's just standard next token prediction loss. But at training time, it's using meta-learning to find the perfect starting point, the best initialization for that test time learning.
And the results seem to give you the best of both worlds. For a 3 billion parameter model, they're basically matching the performance of full attention all the way out to 128K tokens.
But, and this is the key part, it does it with constant inference latency, O1. At 128K context, it's 2.7 times faster than full attention.
Production speed with transformer performance, that's the headline.
It is. So let's dig into why that conceptual shift was even necessary. Let's talk about the long context bottleneck.
Right, so if you're working in this space, you know this pain point. The standard transformer is incredible at what they call nearly lossless recall. You put a token in, and theoretically, the model can see it perfectly no matter how far back it was.
But that perfection, it costs you a lot. Full attention has to scan the keys and values of every single previous token.
That's the O of t squared cost for prefill and O of t for decode. And when t, the context length, gets really big, it just breaks.
It becomes computationally prohibitive. You just can't run it in a real-time system.
So that's why we've seen this explosion of other architectures, right? The new RNNs like Mamba 2 or gated delta net.
And they solve the speed problem. They do. They get you that O of 1, that constant cost per token. Doesn't matter if it's 1K or 100K context. The next step takes the same amount of time.
But the paper's data, particularly in Figure 1, it just lays the trade-off bare.
It really does. While those RNNs are fast, their performance, when you measure it as the loss difference against full attention, it gets worse and worse as the context grows. They just can't seem to compress all that information effectively.
So we're stuck. You can have high performance, but it's slow and scales quadratically. Or you can have low latency, but you sacrifice accuracy on long sequences.
This is where they took a step back and used this great human analogy. Think about a 3-hour lecture you went to 5 years ago.
Okay.
You don't remember the exact words the professor used, right? Or what color their shirt was.
Definitely not. I remember the core ideas, the gist of it, the intuition.
Exactly. The compressed meaning. You didn't do a lossless scan of your entire 5-year brain state. You compress that knowledge into your long-term memory, into your own weights, so to speak.
So that's the shift. Why are we forcing the model to do this perfect lossless recall when a compressed intuition learned over time might be all it needs for next token prediction?
Why not use the massive capacity that's already there in the network weights? And so the whole problem becomes one of continual learning. The model just has to adapt to the specific document it's reading right now.
Okay, so let's break down how that actually works. You said there are 2 loops. Let's start with the inner loop, the test time training part.
Right. So imagine the model is reading a long document. It takes a chunk of tokens. It uses its current weights to predict the very next token.
Standard stuff.
Standard stuff. It calculates the error, the cross-entropy loss, just like in pre-training. But here's the key. It doesn't just throw that error away. It immediately uses it to take a little gradient step. It updates its own weights right then and there.
It's learning as it reads, a self-correcting mechanism. But this idea, like dynamic evaluation, it's been around for a while, hasn't it? What makes this different?
That's a great question. Because those older methods, what the paper calls TTT naive, they had a fatal flaw, this initialization mismatch.
Just match.
They trained the initial weights to be perfect before any updates. It didn't account for the fact that those weights were going to be immediately changed by the test time training process.
Ah, I see. So it's like you train an Olympic sprinter for the 100-meter dash, but then right at the starting line, you tell them they have to run it with ankle weights on.
Precisely. The training objective didn't prepare it for the actual race conditions. And the paper shows this really clearly. TTT naive barely does better than a model with no long-term memory at all.
So how do you train a model to be good at adapting? I'm guessing that's the outer loop.
That is the outer loop. It solves the mismatch with meta-learning, which is basically, learning to learn. So the goal during pre-training isn't just to minimize the loss on the input data. It's to minimize the loss after the model has already done its TTT updates on that data.
Wait, hold on. Let me just make sure I'm getting this. For the listeners, this means to calculate the training loss, you have to first run the inner loop, do the TTT gradient step, and then calculate the gradient of that whole process with respect to the original weights.
You're computing gradients of gradients.
That sounds computationally brutal.
It used to be, but modern frameworks like PyTorch and JAX, they can handle this backpropagation through the optimizer pretty efficiently now. It's what makes the whole thing possible. It ensures those initial weights are the absolute best starting point for adaptation.
Okay, but let's be practical. If you're processing 128K tokens, you can't be doing a gradient update after every single token. That would be so slow.
You can't. And they don't. They use mini batch TTT. So instead of a batch size of 1, they use a bigger batch, say 1,000 tokens. This gives you way more parallelism and stability.
But doesn't that create a new problem? If you're in a batch of 1,000 tokens, but the weights don't update until the end, by token 900, hasn't the model basically forgotten token 1?
You've hit on the exact tension. Within that mini batch, the model becomes a picogram again. It has no long-term memory. And their solution is actually really elegant. They embed the whole PTT process inside a transformer that has sliding window attention, or SWA.
So the SWA is like a short-term memory buffer.
Exactly. It's the bridge. The window size, let's call it K, has to be bigger than or equal to the mini batch size, B. In their setup, they use an SWA window of 8,000 tokens.
And the TTT mini batch is 1,000.
Right. So the SWA provides enough local context for the model to work with inside the batch. Then once the 1K mini batch is done, TTT fires, the gradient step happens, and the long-term memory, the weights gets updated.
It's a real two-tier memory system, SWA for the short term, TTT for the long term.
And making that stable required them to be very, very careful about what they were updating.
It's not the whole network, is it? I imagine if you're adapting everything on the fly, you risk, catastrophic forgetting or just total instability.
Oh, absolutely. So they froze a lot, the embedding layers, the normalization layers, and really crucially, the attention layers themselves.
So the SWA mechanism is static.
It is. The only thing that gets updated during TTT are the MLP layers, the feed-forward blocks.
And even then, I saw they were pretty conservative. They only applied TTT to the last quarter of the blocks. So for their 760M model, that was just the final 6 layers out of 24.
It's a trade-off, a classic efficiency versus capacity problem. Updating more layers gives you more space to store context, which gives you slightly better performance.
But it costs more compute to do the backprop.
A lot more. Their ablations show that updating 12 layers instead of 6 gave a tiny benefit for nearly double the cost. 6 was the sweet spot.
And they also added something to protect the model's existing knowledge, right? They called it safe storage.
Yeah, this part is clever. In those last 6 blocks that get updated, they add a second static MLP layer. It's trained during pre-training and then frozen forever.
Ah, okay. So one MLP is busy adapting to the new document, compressing it into its weights. And this other frozen MLP is the safety net. It holds on to all the general knowledge the model learned from the pre-training data.
Exactly. So the model doesn't forget how to, be the language model just because it read a long PDF.
That makes sense. So what about when it's time to generate text? You're decoding a summary or something. How does TTT work then?
It follows that same mini-batch logic. The model starts generating tokens with its current weights. It keeps going until it's produced a full mini-batch worth of tokens.
And then it updates.
Then it takes a gradient step, updating its weights based on its own output. It's a form of self-training. And then it continues decoding the next batch with those newly updated, more context-aware weights.
Which brings us back to those incredible results. Looking at figure 1 again, the fact that the TTT E2E performance loss stays flat relative to full attention from 8K all the way to 128K, that's the proof.
It proves the mechanism works. It's actually leveraging that extra context by embedding it in the weights, which is something those RNN architectures just couldn't do effectively.
And you get that O1 constant inference latency, 2.7 times faster at 128K. It just feels ready for production.
And it uses standard transformer infrastructure. You don't need custom kernels. That's a huge deal for adoption. You can use all the existing tools for optimization and sharding.
But the most counterintuitive result for me was in Figure 6, the loss breakdown. It says TTTE2E actually gets its biggest advantage over full attention on the earlier tokens in the context. How does that work? Why is the adaptive model better at the beginning?
This is where that meta-learning outer loop really pays off. Think of it like this. Full attention is a student who has to study for every possible test for the entire year all at once.
Okay, so its initial knowledge has to be very general.
It has to be a good generalist. Its weights are spread thin to handle any possibility. TGTE2E, on the other hand, is a student who's been trained to be a master specialist, but only for the very first quiz.
Because it knows it can study and adapt before the second quiz.
It knows it gets to adapt. So its initial weights, the W0, they don't have to be good for the whole sequence. They just have to be perfect for that first mini batch. It's a much easier, more focused task.
And that focused optimization gives it lower loss right out of the gate.
That's the theory. And the data shows this approach scales just like full attention when you increase training compute. So it seems robust enough for those really big production level models.
Okay, but we have to talk about the trade-off, the big one. TTTE2E is clearly amazing at compression. But what happens when you test the one thing full attention is designed for?
Nearly lossless recall.
Exactly.
And for that, we have the needle in a haystack task, the NIAH benchmark. Can the model find one tiny irrelevant fact buried in a sea of text?
And the results, they are not subtle. Table 2 shows it plain as day. The standard transformer with full attention just crushes TTTE2E on these tasks.
It's the price of compression. Full attention keeps an explicit copy of the whole history. TTTE2E distills it into an intuition. It loses those ultra-fine-grained details.
So if your application relies on retrieving, a specific taxcon from a 100-page document, TTTE2E might literally forget it, even if it understands the overall meaning of the law better.
That's a crucial limitation to understand. And there's one other big practical limitation, which is the training cost.
Right, we talked about the inference efficiency, but that meta-learning, the gradients of gradients.
It's expensive. At the 8K context length where you do most of your pre-training, TTTE2E training is 3.4 times slower than training a standard full attention model.
Wow, that's a massive hit. You're basically shifting the computational burden from inference time back to training time.
You are, but the authors suggest ways to mitigate that. One is hardware custom kernels that are optimized for this specific computation.
And
the other is transfer learning. You could take a standard pre-trained transformer, one that's already been trained on billions of tokens, and then fine-tune it with the TTTE2E meta-learning objective at the very end.
So you minimize the time you spend on the really expensive part of the training. That's clever.
So yeah, at the end of the day, it's a really successful implementation of this memory hierarchy. You have SWA as the short-term memory, and the adaptive weights as a compressed long-term memory. It's a huge step forward.
And the power of that learning at test time. It's profound. The authors mention that data quality and even tokenizer choice have a huge impact on how well TTTE2E learns from the context it's given.
Which, when you think about it, opens up a really fascinating door for future work. TTT is the model taking responsibility for its own learning during inference.
So what if you gave it more control over that process?
What if we introduce a layer of critical thinking? Instead of just training on the raw input mini-batch, what if the model first generates a summary? Or a filtered, rephrased version of that mini-batch.
And then trains on its own higher quality output.
Exactly. You could act like a gating mechanism like we see in sophisticated RNNs. The model could actively decide what information is important, what to protect from being forgotten, and what to compress.
If it could generate a really dense, high-quality version of the context and train on that, it might get even better at retaining information. Maybe it could even start to close that gap on the needle in a haystack tasks.
Without sacrificing that O of 1 speed, it feels like the convergence of test time training, meta learning, and this kind of active self-generation. That could be the next really big leap.